do reactive power compensation. So the circuit of this is look like this. So I draw the circuit so they can get a good understanding of it. So this is the substation that we have right here. And then we have a load which has a P plus JQ. And then it draw a current I here with a magnitude of 10. And then with an angle of minus 30, okay? So in order to support that, we actually have the grid sending the real power and reactive power to it. So if we do reactive power compensation, that means that we will connect it to here a capacitor bank so that the reactive power can be partially or all of them can be provided by this capacitor. So this is the C, the capacitor here. So in this demonstration, we're computing the capacitance needed to provide this reactive power in order to correct the power factor to a targeted value. Okay. So you can see that from this view graph, just move it over to here. You can see the setup of it is we have the RMS value, which is 120. And then we have the angle, which we use the voltage here as a reference. So here we have 120, and then this would be 0. So that's the voltage at this bus, okay? So this is the V equals to that. And then we have our current, RMS value equals to 100. So this another one, 10 is 100. This would be 100 with an angle of minus 30. Minus 30 right here. So first, we want to convert the polar value, which is this, to a complex number, which is right here. You can see 120 plus J, 0 times J omega. So we can use the RMS value times the cosine angle, and then plus the sine angle times 1J, okay? One thing, as we mentioned before, if our angle is represented in degree, then we need to use degree to radius to convert this angle from degree to radius. So this is one way of doing that. So the other way of doing this is we can use EXP instead of this whole thing, okay? We can actually simplify this whole formula into this EXP because this is because the EXP J theta, it equals to cosine theta plus J times sine theta, okay? So this is why this whole expression here can be represented by this one, and then this whole representation here can be expressed by this one, okay? So from the result, you can see that they gave us a similar result, okay? Like this, they're the same. Okay. So next, we're going to compute the complex power. We have V and then we have I, and then V times the conjugate of I equals to the complex power. So the real part of it would be the real power. The imaginary part will be the reactive power. So those are the real and the reactive power consumed by the load. So if we want to compute for the impedance here, so this impedance right here, then we can simply use Z equals to V divided by I, okay? So that's exactly what happens here. And then we have this kind of omega. This is because we need to compute it for C. And then for C, we can see that the capacitance and then the reactance of a capacitor can be computed by using 1 divided by omega C, okay? So the capacitance can generate a reactive power, and that can be represented by the voltage across this reactance. The voltage across it is simply be this value, right? And then divided by XC. XC equals to this, so you can put them right here. So if that's the case, then this would be divided by omega C over 1, okay? So omega c over 1, it could be represented by this. Okay, so let me just try this. So this will simply be, move this over, so that's 1 j omega c. Okay, so we can ignore the c if we want to compute the magnitude of the power. So we can use this, and then the magnitude of that will simply be taking this j off, and then you can see that this is how we compute the reactive power. So once we know the reactive power need to be consumed by the capacitor, then we can compute for the capacitance by moving this part here, right? So simply be this value divided by that. So that's how we can compute the reactance over here. So now you can see, I'm going to keep this equation so you can see it. Okay, so this is how we're going to do the rest of the computing. So you can see that if we want to correct the power factor to 0.9, then what we'll do. So we do an iteration because we have a number of target value we want to compute. We want to see if we want to correct the power factor to 0.9, 0.95, 0.99, and 1. What are the capacitance needed to correct them to this target power factor, right? So one thing that we need to notice is for this correction process, the real power consumption will not change because this capacitance will simply be providing the reactive power. So what is unchanged is this p-value. It is unchanged. So if we want to compute for the new power that need to be provided by the grid, then we can just say, hey, if from here, our power factor is corrected to 0.9, then I can simply use p divided by 0.9, right? So that would be the new s value, and then times square root of 1 minus 0.9 squared, and then that should be the new q needed, which is this value, okay? So once we have this new corrected the q, we know that this q cap plus this q equals to this q load. So the q cap simply will be equals to the q load, which is this one, minus this whole thing, okay? Okay, so this would be the Q corrected right here. So this is exactly what we have done here. We use P divided by this targeted power factor, and then times the square root of 1 minus the corrected power factor, which is 0.9 squared, okay? And then we use the Q, which is the load consumption right here, minus the Q corrected. So that should be the capacitance, the reactive power generated by the capacitor. So this way we would be able to use this equation because we already know the Q cap right here. We already know the Q cap, okay? The Q cap is computed from right here, and then divided by the V squared divided by omega. So this is how this equation is done, right? So once we calculate that, you can do a do another round of verification. You simply use this capacitance. So this 1 divided by J times omega times the C, and then you use V divided by this Z cap. That will be the current flowing through the capacitor, and then you can use the conjugate of the I cap times the V to see if this value you calculated equals to this Q cap you need. Okay, so this is how you do one iteration. And then when this iterated to the third value, then we will compute it for the capacitance for needed for correcting the power factor to 0.95. So you can see that the reason we need to use this I here is because we want to keep a record right? So normally when you do that, you want to actually initialize those values. For example, Q cap equals to zeros. And then if you want them to be the number of points, because that's how the matrix should look like. So this way the MATLAB will assign a matrix to it. It will expedite your computing. Okay. So for all these values, we can give it the initial value. So this is also something we use. So we can just put it here. And then there's another value here we use a cap. So normally when you do this, you can initialize all these values. So the MATLAB will know before it ran into this iteration what would be the size of the matrix it's assigned to. Okay, so we can do this. So this way we will initialize all these values. So we can run that. Okay. So this way you can see that this is the first figure I got. Basically what we have done is that we plotted out for different power factor here. What would be the capacitance needed? So the first point here, the first power factor is the original one, which is the PF. That's the original power factor. So we don't need any capacitance there. Okay, so that's why we started with 0. And then to correct the power factor from the PF originally is 0.866 to 9. Then we need a capacitance of about 200 microfarad. So you can see that when I plot them out, I times this capacitance by 10 to the power 6. This is because this original value would be in Faraday. So in order for us to see not times 10 to the minus 6, let's just do that. Without this, you will see. Then this will be 10 to the power minus 6. And then this value would no longer be microfarad, okay? So it will be Faraday. Let's run out. Okay. But usually this is harder to see, so I will just put the mu here in there, and then I'll times this by 10 to the power 6. So this will convert Faraday to microfarad. Okay, so when you run it, you can see that this label here will become 1,200 microfarad. Okay, so this you can see that when I correct the power factor to 1. The capacitance I need will increase. Okay, so the next thing that I want to see is what are the power provided by the capacitor. So this red line is original load consumed power, reactive power, and then this is the capacitor provided power. So eventually you can see when the power factor equals 1, all the load consumed reactive power is provided by this capacitance. Okay. The next thing that I want to see is how this grid power changed. So this blue one is the reactive power. Let me show you that. So the blue one is actually the S here, okay? And then this red one is the P, and then this origin one is Q. So you can see that initially the grid provided both the P and Q. And then for when I corrected the power factor to 0.9, although I still provided the real power, but I provided less power from the grid. This is because part of this is provided by the part of these here are provided by the capacitor. And then you can see that here, the capacitor provided more and more power. I just kind of draw a straight line. So you can see that when you have more and more reactive power provided by the capacitors, eventually the grid provides 0 reactive power. So this way, you don't have to let the grid send a lot of power over. So this will reduce the losses along the way, and then also reduce the current needed from the grid. So this current will be reduced. And then because the grid only need to provide the real power, so along the way there's less losses as well. Okay, so this is the value why we need to do that. The other thing we want to see is actually it is the voltage drop. You can see that when we have to maintain the voltage at this load to be 120, so this is a load. Suppose that we have this is the other side of the grid. There's a power drop, right? Suppose we have a impedance somewhere here, and then to maintain the voltage at 120. If we have the grid sending the reactive power, then I need the grid to actually send me a lot more. We will have a voltage drop across this part, okay? So this is why when we do the reactive compensation, you can see that the power, if we do reactive compensation, you can see this is initially the power factor. So that means at this part of the grid, the voltage needs to be much higher. But if I provide the reactive power locally, okay, the drop along this resistance will be reduced because there are less current passing through this resistance, this impedance. So by doing the reactive power compensation, I literally do not need to maintain a high voltage at this grid high side, okay? So that way it will also be beneficial because there are less voltage drop along the way, okay? So have a less requirement for maintaining a higher voltage at the sending end, okay? So you can play with this code a little bit just to have a few points. Like first of all, I want you to learn how to use bar plots. You can see that the bar plot can give us a good visual effect. So we can see from here what would be the power sent by the grid, and then what would be the real power, and then the reactive power component of this complex power. Okay, so this is the bar plot, what can be done. And then the other thing is how to use legend. For example, the legend would tell us that this blue one is the grid power, and this red one is the real, and this orange one is the reactive power. Okay. The other command I want you to learn is this for loop. When you have a number of values, you definitely can try to use this. For example, if I use more, I can just say 1.001. So this will give us a lot more intermittent values, 1.0. And then if I do this, then that again. So this way I can see a lot more points in between, okay? I can see that from 0.9, then every 0.01 incremental, then how many points that I need, okay, for the reactive power I provided. So that way I would be able to see when I correct the power factor to 0.9, 0.91, 0.92, what would be the capacitance needed. So by doing this loop and then using this matrix representation, you can do a study to see incrementally how the incremental needs are for different power factor correction, right? So I think this is a good thing for using the for loop. And then when you use a for loop, if you want to keep some value, you need to use this index so that it stores in this like one by one. This is the first iteration, second, third, and then by doing that, you better initialize these matrices because before you run it, you know it's going to run this many iterations. So you just initialize this vector to the size of the number of iterations you need to run. Okay, so that's all about this demonstration. I'll see you next time.